Alright, silly people, here's the situation. We are tasked with proving that the time derivative of the integral of two wave functions multiplied by each other, psi1 star psi2 um, dx, is equal to 0. Um, so the way to do this is to actually um, move that time integral in there. Say it's del t of psi1 star psi2 integrated over dx. Um, and then expand that derivative using the product rule. You'll say this is going to be del psi1 star del x, or del t actually, times psi2 plus psi1 star del psi2 del t. All of that integrated over x. So I'm just going to put some braces here. Dx. Um, at this point, it's useful to write the Schrodinger equation, which is valid for wave functions like these. So that is going to be just I h bar del t of psi is equal to minus h bar squared over 2m del squared del x squared psi plus v psi is equal to, yeah, that's it. That's the time-dependent Schrodinger equation. You can also write the complex conjugate of the Schrodinger equation. It's equally valid and necessary for this problem. Plus v psi star. And then just plug these into our integral now. So it's going to be the integral from minus infinity to infinity of, you're going to have I over h bar for all of this, actually. So I over h bar. And then d psi 1 star dt will become minus h bar squared over 2m del squared psi 1 star del x squared plus v psi 1 star. And that's multiplied by psi 2. And I'm just thinking about if I got the sign right. Yeah, I did. Okay. And that's going to be minus psi 1 star minus h bar squared over 2m del squared psi 2 over del x squared plus v psi 2 dx. So, first we're going to collect some terms. So we'll collect terms that are dependent on just vi over h bar. You're going to have the integral of, it's going to be psi 1 star psi 2 minus psi 1 star psi 2, which is 0. So don't even worry about it. Then collecting terms that which depend on I h bar over 2m, yeah. I h bar over 2m. We'll make it positive. Yeah, so that's going to be psi 1 star del squared psi 2 del x squared minus del squared psi 1 star del x squared psi 2 dx. So, I mean, now that this is 0, I'm going to write this in a way that is a little bit more suggestive of what we're actually going to end up doing. So you'll have IH bar over 2m. We'll open a bracket, and then we'll send minus infinity to infinity, psi 1 star del psi 2 del x. That's squared dx minus the integral from minus infinity to infinity of psi 2 del squared psi 1 star del x squared dx. And we're going to do integration by parts on both of these at once. And so for the first one, we're going to have u1 equals psi 1 star. So the differential du1 is going to be the partial derivative of psi 1 star with respect to x times the differential dx. And then we'll have dv1 equals del squared psi 2 del squared x dx, and the integral of that is through the fundamental theorem of calculus, actually, just del psi 2 del x. And then on the integral that's on the right, we're going to be doing the same shit, but now we're having u2 equals psi 2, du2 equals del psi 2 del x dx. You're going to have dv2 equals del squared psi 1 star del x squared dx, and then the integral of that is del psi 1 star del x. So after doing that, we can rewrite our integrals. The form for integration by parts is given by uv, so we'll have psi 1 star del psi 2 del x evaluated from minus infinity to infinity, and since we know that wave functions converge to 0 at minus infinity and positive infinity, this will just go to 0, so no worries about that. You'll have now minus the integral of v du, so it's the integral of del psi 2 del x del psi 1 star del x dx. And then the second integration by parts will actually have a minus sign thrown onto it, will be uv, so del psi 1 star del x psi 2 evaluated from minus infinity to positive infinity, which also goes to 0 because, again, wave functions converge at minus infinity to positive infinity. And then finally plus this integral minus infinity positive infinity of v du, which is psi 1 star del x times del psi 2 del x dx. And look at that. These two expressions are the same. So they also cancel out. So the whole thing is 0. So that the proof is good. Funny problem.